So if I have two charge planes, using the same idea that you would get from a charge line, you can begin to see that the electric field, if I want to calculate it at some point over here, I'm going to be able to find a charge on this side of the plane and a charge on this side of the plane, which would once again produce a field that points away from the plane. So for a plane of charge 2, from symmetry, you can conclude that the electric field due to a positively charged plane is going to point away from the plane in both directions. So if I were looking at this edge on, so if I'm looking at the plane from the side rather than from the front, the electric field due to this plane is going to point away from it in both directions. And this is true everywhere on either side of the plane. Okay, what is the magnitude of the field? That, again, we don't have the tools to calculate without doing calculus. But if you do go through the calculation, you get a very simple response. So if I have a plane which is pretty big, so you notice the word large and uniformly charged. That means the charge distribution everywhere on the plane is the same. So if I take any patch of area A and I count the total charge in that patch, if I take a different patch of the same area, I'll get the same amount of charge there. So the amount of charge per unit area is constant everywhere. Okay, so then I can express the field magnitude in terms of the charge distribution. So you notice the thing over here is charge per unit area. So really what matters is not the total charge and not the total area, but the fact that that charge is uniformly distributed everywhere. So you get two interesting results here. One is that the field depends on the charge per unit area. There's a factor of 2 here. There's another constant epsilon naught, which I'll explain in a second. But you notice that there is nothing in this formula that talks about a distance from the plane. There is no r, no distance x or y or z from the plane. So this means this field strength is independent of how far you are from the plane. It's a constant field. So on either side of the plane, it's not constant when I go from one side of the plane to the other, but if I'm on the right-hand side of this charged plane, the field everywhere, all these vectors are the same length and pointing in the same direction. Doesn't matter how far I go. So this is an approximation, of course. It assumes an infinite plane. But it works reasonably well if the plane is large and I'm very close to it. So if I, don't go too far from it, this approximation works well. For all intents and purposes, we can assume that the field of a charged plane is a constant field. So it creates what's called a uniform electric field. A uniform electric field refers to the fact that the electric field is of constant magnitude and direction. It is the same electric field everywhere. Okay, and this creates a uniform electric field on one side of the plane. Okay, on the other side of the plane, the magnitude of the field is same, but the direction is changed. And the direction is such that it points towards a negatively charged plane on both sides. It points away from a positively charged plane on both sides. Okay, what is this constant epsilon naught? So remember the constant k we had used? We had k is equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared in Coulomb's law. So this new constant is related to that. Its k, it can be written as 1 over 4 pi epsilon naught. Or epsilon naught is 1 over 4 pi k. And so when you do that, you get this number, 8.85 times 10 to the negative Coulomb squared per Newton meter squared. This is a constant called the permittivity of vacuum. Okay, so it's an alternative. Actually, physicists don't use the constant K, they use the constant epsilon naught because it's a more fundamental constant in some sense. And I'll tell you why that is. That's because this has one value in vacuum, and it tells you something about the strength of the electric field in vacuum. So remember, we have Coulomb's law due to a single charge or due to a pair of charges. F is equal to K Q1 Q2 over R squared, which is 1 over 4 pi epsilon naught, if you like, in terms of this new constant, Q1 Q2 over R squared. So this tells you that if I have a force between two charges in vacuum, this is the constant that happens. But if I put those two charges in another material, in a medium, okay, that constant changes. Okay, and it becomes a constant that's characteristic of the material. It's called the dielectric constant of the material. Okay? And why is it different inside a material or outside in vacuum? We'll get some sense of that today when I come back to talking about dipoles. So let me start with the planes, and then we'll go to dipoles, and then I'll explain further what this constant means. So what you need to know for the uniformly charged plane is that the electric field is constant, okay, everywhere. On either side of the plane, it has the same magnitude, but it points away from a positively charged plane and towards a negatively charged.